All right, welcome to those of you who couldn't attend class today. So let me just pull up the slides here. Let me just get full screen mode going. Where is it? There we go. So we're going to do a few things today. The first thing that we're going to do is just a bit of review. And then the second thing that we're going to do is talk about some new material. We're in the phase of the course where we're transitioning from one topic to another topic. The first topic that we have covered is this notion of probability theory. So we talked a little bit about what is probability, what are distributions, what are expectations, what is variance, how do we take the expectation of a transformation of a random variable. These are all things that we've covered. We have one or two more things to cover, in particular how to deal with transforming random variables. And then after this, we'll transition into a new part of the course. That new part of the course won't be as much on probability theory, but instead it's going to be more on statistical inference. So it's going to be more on modeling real data, and that model of the real data itself will be random in interesting ways, and we'll learn about that. We'll learn about what statistical inference means. We'll learn a little bit about things such as asymptotic inference. You'll be able to do some of that, and we'll be able to think together about some of that, and we'll have some fun with that. So we'll get the second part of the course is more about working with the real data. The first part of the course is more about the conceptualization and so forth and so on. But the two are linked in ways that we'll talk about. Since something called a p-value is, you need to understand something about probability. You need to understand something about different distributions to understand what a p-value is doing in many cases. So we'll go through that, and everything will be brought together into a nice cohesive whole. So this is what we're going to do today. We have some review questions, but I'm going to skip these since I think they're similar to what we had before. And this is just what we had last time from our section on conditional probability. So I'm just going to skip over this too unless we have any questions. This is just sort of getting our minds starting to think about what is statistical inference, or how can we learn about these parameters using data. Since so far we've just sort of assumed that the parameters were something that we knew, but in the real world we don't really know what the parameter is. We don't really know, like for example, the support for a particular policy is. That might be a parameter in some kind of model. We don't really know it. All we can do is get data to learn about it. So there's this process of learning about these unknown things using things that are known. And there are all sorts of problems, all sorts of challenges that come up, and we'll talk about those each in turn. So I think the course gets more hands-on as we go. So that's just a bit of review. These are some of the key principles of probability theory that we talked about last time, and we talked about how they're interconnected in interesting ways, and we also talked about how these ideas can lead to some interesting paradoxes. So we introduced this notion of Simpson's paradox, and we introduced how that can come about, how marginal probabilities can be different in the conclusions we would draw from them compared to conditional probabilities. And that was interesting, and that was something we learned from, and it was a thought-provoking kind of thing. So that's this review, and we have a few more things that I wanted to review before we moved on to some new topic. The topic for today, it can be a little bit abstract at first, so I'm going to introduce it today, and then we're going to talk about it again next time we meet on Wednesday in a way that will reinforce all of our understanding, and we'll be able to go from there. So today I want to just wrap up with this notion of distributions. We've been talking a lot about different distributions, but I felt like we needed to talk a little bit more big picture and a little bit more globally. What are the different distributions? How can we think about them? Introducing you some more of them. Since remember, these are like actors in a story, so let's just get to know a few more actors before we talk about transformations of variables, which is important in ways that we'll understand together in the real world applications that all of you will be building up in your dissertations in just a few years, if not even sooner. So with different distributions, why do we have them? Well, we have different distributions because they're used for modeling different kinds of events. Remember, the sort of things that happen in the world aren't all the same. We have elections, and we have income, and we have wars and protest events. All of these are different sorts of things, and there might be different assumptions, there might be different event spaces, there might be different kind of tailoredness of those different processes. There might be different min and max values associated with them. And all these things mean that we need to have different utensils, so to speak, for dealing with those different situations. It's like in cooking, you don't just have a knife or a fork, you have a fork and a knife because you use your fork to grab and your knife to cut. And it's just like that with different distributions. You have one distribution for modeling data that looks like this, and another distribution for modeling data that looks like that. And these all work together. So those are just a few high-level thoughts for you. I'll just review. There's that notion of tailoredness to the distribution. Tailoredness to the distribution, basically, we talked a little bit about it when we talked about the moments of a distribution. Remember how skewness was how lopsided the distribution was? So if it's right skew, it has a lot of kind of probability mass or probability density to the right of the center point, where if it's left skewed, it's the reverse, and it's lopsided in the other direction. And then there's also this notion of kurtosis or fat-tailedness, and that's it's a little bit different. It's not about the lopsidedness of the distribution, but instead it's about how probable or how likely really extreme events are. So super extreme deviations from the mean, how do those play out in the distribution? That's another property of the distribution called the tailoredness of the distribution, and that's relevant for especially financial modeling or things like that. So if you're going down that direction, I can point you to a few books, I can point you to a few articles or a few courses, but that's all we'll say about it for now, although we may come back to it later in the semester, since it's really relevant for regression modeling. So these are just different distributions, and as you can see, there are a lot of different distributions that people use in the quantitative social sciences. It's not just the normal distribution, it's not just the Bernoulli distribution. I think those two are the most prominent, the most common, the most ubiquitous, but there are others as well. The gamma, the beta, chi-squared, I listed some of them out here. You don't need to memorize, I don't want you to go memorize all the properties of these different distributions, but it's just good to know there's a whole universe of these things, and people work with them in different scenarios. And it's not important to kind of know every single one, but it's important to know the main ones, and we'll talk about a few of the main ones today, and that will be a good transition point for talking about transformations of variables. So that is what we have there. If we end early, I have a few slides on simulation in the quantitative social sciences, which we can use in case we end early. But I don't think we will. I think we have a lot to get through and a lot of concepts to plumb. Okay, so I'm just going to go through and kind of review these different distributions. Well, while I'm talking, I think you should think to yourself, like, what our problem is relevant to my research where I could maybe use this distribution to model some important data source. So the one distribution that we've talked a little bit about is the binomial distribution, and some of this is review by design, since it's always good to review things and make sure you see it a few different times. But the binomial distribution, it's you can use this to model the number of successful elections won by a party out of a set number of races. So if you have, let's say, 50 different, or let's say 25 different Senate races, the Democrats will win some number of those, and the Republicans will win some other number of those. And if you wanted to model the number of seats among those 25 races that the Democrats win, that would be characterized by a binomial distribution, where we have where we're trying to understand or characterize the different possibilities over a number of successes in a fixed number of Bernoulli trials. In other words, we have a bunch of elections. We have 25 different elections. You can think about each election as a quote-unquote Bernoulli trial, coin flip. It's either a Republican or a Democrat winning the election, and we're basically saying how many did the Republicans or how many did the Democrats win. You could model each of those with the binomial distribution. So that's one of the things that we'll talk about as we go. And this is one example. Maybe I should pause and ask, can you think in your own research, is there an application that comes to mind for you in your own project, in your own kind of your own interests? Can you think of a case where the binomial distribution might be relevant?
Choice for a certain candidate in the election?
In terms of the vote counts, or can you say more?
Voting choice.
A voting choice. So you're saying there are multiple candidates, and who do you choose? Is the idea?
If there is two candidates and I have to choose one, then it will be binomial.
Yeah, that would be binomial. There are these two parameters. We have the n parameter, which is the number of trials in this whole sequence of trials, like the number of races. And then we have the success probability, and this is just assumed to be the same for all of the trials. So in that case, the number of trials would be 1, in the sense that we have two candidates, and we're saying, did one of them? We're adding up the number of successes in the context of one race. So how many times did you win out of the one race? And it would just be either 1 or 0. So in that case, the support would go from 0 all the way to 1. But in other cases, if you had, let's say, 100 different candidates, then, well, yeah, I guess if you had 100 different races, then that n would be different. So n is one of the parameters, and p is another of the parameters. And these control the probability of different things happening. This is the p. This should read PMF there in the slides. The PMF can be written out like this. This thing that looks like that, this n, then underneath it x, that's known as the binomial coefficient. You can use R to calculate that. There are also tables for calculating that, or there is a manual formula for calculating that. So that's just a weighting factor. And then you see that this p also enters, and then you also have this n here. So in this formula, you have n, you have p, and then you have an x. And x is the thing we're trying to evaluate. We're trying to say how many, what's the probability that the Republicans win 25 out of 25 of the races. In that case, x would be 25. N would also be 25. But if you wanted to instead model the probability that the Republicans win 2 of the races, then n would still be 25, but now x would be 2, because you're saying what's the probability that they win 2 of the 25 races. So that's, we have a question.
Oh, I was just going to say another example.
Oh yeah, please. What's another thought?
Another example would be like successful democratic revolutions or successful regime changes in a fixed set of time, like the Arab Spring. Be how many successful regimes were overthrown, or democracies, and then below if you just did democracy.
Yeah, no, that's a great example. Another example, yeah, like you're saying, would be if you have revolutions, you have a certain number of attempted revolutions, and some of them are successful, and some of them are horrible failures, and you could use the binomial distribution maybe to characterize that. One potential problem or challenge would be characterizing the set of total possibilities. In some cases, that might be easy to do if we have, let's say, a certain number of elections that we know about, but in other cases, for other kinds of data, it might be harder. So if we're looking at protest events, in that case, maybe the number of trials, so to speak, might not be clear. Is it this or is it that? It's not exactly clear. So that's just one thing to keep in mind when you're thinking about different distributions. We also have different properties of the distribution. Remember the expected value and the variance. We could compute these on the board just like we did before with some of the Bernoulli distribution properties. I'm not going to do so now. I'm just going to go through a few different distributions so that we have them in our playbook, so that when you face them or when you read about them, you'll know what they are. But here are a few of the properties. You can see that as the number of trials goes up, so as n goes up, the expected value of x goes up too. In other words, if you have more and more elections, the probability of successful, of electoral victories goes up too, which makes sense. If you're thinking about a country you would expect that all else equal, the Republicans would win in the context of a situation where there were 1,000 elections compared to when there were 10 elections. The more elections you have, the more elections that you're expected to win, all else equal. And also P, it depends on, the expected value depends on P too, which is another parameter which in this case basically tells us as the probability of success in any single race goes up, the overall number of victories is expected to increase too. So it's always good whenever you see a new distribution, try to ask yourself, does this make sense based on what I know about what this parameter is supposed to be, or am I not understanding something? And you should try to use that as like a mental guide. So this is the Bernoulli distribution, and I'll go through the others a little bit more quickly. We also have the beta distribution, which is used for modeling probabilities. So in some cases, you might know what the probabilities of a certain event are, But in other cases, you might not exactly know, and you might want to actually model the probability of the probability. So it's sort of a meta-level distribution where you're saying what is the what is the uncertainties over the support for a particular policy in terms of population. So the population might have a certain level of support for something. That support can be characterized like as a fraction, as a probability between 0 and 1, and we might want to understand the uncertainty over that, or we might want to understand these beta distributions also get used in the context of topic modeling. A generalization of the beta distribution gets used. So you can think about modeling probabilities where there's just one event involved, like a coin flip, but there's also a situation where there might be multiple events involved, and in that context we use something called the Dirichlet distribution to model that. So sort of a generalization of the beta distribution to model probabilities over higher dimensional spaces. So that's something that you'll see perhaps in the text analysis course, perhaps in the machine learning course. We might go through it, we might cover it because it's coming up. I was just reading a new paper today on topic modeling, and they're talking about the Dirichlet's, they're talking about the betas, they're talking about these things. So we should try to understand them too. Here's the PDF. So in this case, the support should read 0 to 1. So basically, X here is like a probability. And remember, probabilities go between 0 and 1. So the support is between 0 and 1. And here is the PDF for the beta distribution. So it's a little bit more complicated, but there's a certain similarity to what we had before. So if you go back to the binomial distribution, you can see there's a p to some power, and then there's a 1 minus p, raised to some power. And we can see kind of the shadow of the binomial PDF within the beta distribution formula. Since you see this x, times 1 minus x. Here, x is sort of, in a certain sense, playing the role of p before. P was a probability before. Here, x is a probability. Before, p was fixed. But now the probability was fixed, and we call it p, and it was a parameter. Now the probability is not fixed, and we call it a random variable. So there's a subtle shift in perspective, and that gives you some sense for the similarities and the differences between the different distributions. And I think this is a good example for your own mind to test yourself. Like, do I really understand the difference between quote-unquote a parameter and quote-unquote a random variable? This distinction becomes very important in the second half of the course, which is on statistical inference, which is all about learning about parameters from data. And in that setting, the parameter will be some fixed known quantity, but we're going to estimate it. And the subtlety there is that the estimate is random. It's a function of random data, but the parameter itself is not random, and it's some true thing existing somewhere that we're trying to learn about. So there's a subtle distinction there, and this gives you some example of that. So we have an alpha and we have a beta parameter. These are both shape parameters. There's not a great intuition for these compared to in the other case. These alpha and beta parameters have to be, I believe they have to be positive real numbers. So they can't be negative, they have to be positive. And you can throw them into this equation, and you can get the expected value of this quantity, and you can also get the variance of it. In the expected value, you can see that if you just take a look at the expected value, you can see that it's going to be between 0 and 1 for the same reasons. It's like alpha divided by alpha plus beta. So we're going to see that this is going to be between 0 and 1, the expected value. We also have the variance, which is a bit more complicated. But yeah, these are two important distributions: the binomial distribution, the beta distribution, and we also have another distribution called the exponential distribution. I'm going to go through this one a bit more quickly since the intuition is a little bit less important here. But the key insight here is that sometimes you might not be modeling the count of events, but instead you might be modeling the time it takes before something happens. So in some situations, like for example, protest events, you're interested in modeling how many protest events happen in a specific interval. And some people use the Poisson distribution to try to model that. Well, you can kind of flip the question on its head and ask yourself, how long are we going to have to wait before the next protest event, or how long are we going to have to wait until the next assassination attempt? These are all things that we can think about, and the exponential distribution is used to model those. In this case, the support is between 0 and infinity. So in other words, you could wait just a millisecond, or you could have to wait until 100 years or 100,000 years or a million years. You could wait a boundless amount of time. So that's what I would say about that. And then here's the formula for it. Yeah, so this is that. The lambda parameter, it tells you, so this lambda is related, if you remember back to the Poisson distribution, the lambda there is basically, in a certain sense, the same as the lambda here. When that lambda controls the kind of the frequency rate of this underlying process. So if we have some process like protest events, there's some inherent frequency rate, and when that frequency rate gets higher and higher and higher, you can see that the expected value of this waiting time gets lower and lower and lower. The idea is if that frequency rate gets really high, that's basically, you won't have to wait very long until the next protest. They're protesting every day, they're protesting every minute, they're protesting every second. Whereas when that rate gets lower and lower, when that rate gets smaller, then you have to wait longer. So the idea is this lambda here is in a sense connected with the lambda in the Poisson distribution, and you can see the connection there through this expected value, which is just an interesting connection. And we can talk more about that, and in other courses I'm sure we'll get into it as well. Any questions, any comments? Can anyone think of any in your research, would this be relevant? Can you think of a time when this might be something you would want to use? I guess another thought would be, I know a lot of folks might be studying constitutions, and the amount of time, between one constitutional override and the next, or one constitutional reform and the next, that could be modeled potentially with exponentials. So that'd be one example. Very good. And then the last one, so this is a bridging example, which is going to, in a sense, give us entry into the new topics for today, which is about transforming random variables. So the log normal distribution is another kind of distribution, and it's interesting because it has the following kind of motivation. If x is normally distributed, then e of x is log normally distributed. So in other words, in some situations, in some situations our data have to be positive. For example, income. You can't have a negative income, at least in most cases. So things can't be negative, and they have a right skew to them, meaning like for income, you have most people who make around, I guess, 70,000 is around median income today in the US. You have most people who are kind of centered around there, but then you have some people who have millions or hundreds of millions or billions or even hundreds of billions of dollars at this point. So you have a really long right tail of that distribution, a lopsidedness to the distribution, and in that case you might think that the log normal is a decent approximation for that kind of data. So in other words, the data they have to be positive, they can't be negative, but so in a certain sense it's like we had some random variable x and we raised it some power. So this is a random variable present in a lot of data, a lot of modeling of economic variables, economic changes, and so forth. We have two parameters here, which we call mu and we call sigma. And you can think of these as the mean and the standard deviation of the normal distribution that you're taking the exponentiation of. So remember, when you're raising something to the eth power, you're basically saying, you're raising it to a power, and it has to be positive. So when you raise something to like 10 to the first power, that's 10. 10 to the second power, that's 100. 10 to the third power, that's 1,000, and so on and so forth. And you're doing the same thing here, but now the base, instead of 10, is e. But you're doing that same sort of exponentiation. So you can model similar sorts of kind of processes like we see with income. And we'll talk a little bit more about that later on. The support of this distribution is between 0 and positive infinity, so it has to be in that range. And here is the PDF for this distribution. We also have a mean, and we also have a variance. And you might ask yourself, how would we be able to derive something like this for ourselves, or how would we at least be able to understand the reasons why this was what it was? So that motivates the second part of the first part of this class, which is all about transforming random variables. So let's say that we knew what x was, but we didn't know what the distribution of e of x was. we might want to learn about that. So an example. So here are the distributions over income across the world. You can see the U.S. is there on the right-hand side. And it takes up, in terms of GDP per capita, it's a pretty big number. I guess it's about $50,000 in this data from the 2014 purchasing power parity adjustment. So purchasing power parity is we're trying to adjust for the fact that different places have different living expenses, essentially, and we're trying to adjust for those factors. And so some places have a lot more GDP per capita than other places. Like Ethiopia is way over here, and we have some that are even less well off in terms of GDP per capita. So we have this distribution where it's not all centered around the average. The average GDP per capita is around the GDP per capita of Brazil, but you see that there are some places with a lot more GDP per capita than that average, and this characterizes a kind of a lopsided distribution, and this characterizes a distribution that we might want to model not using a normal distribution but using something like the log normal distribution. So how would we think about transforming this data into something that looks normal? So in other words, here if we have something that looks maybe our data is E of X, maybe that's the data that we got. But could we take the log of that to somehow get back X? Like, this is the kind of thinking that we'll get through. And this is going to come up in regression a lot too. Since in regression, we're going to want to a lot of times transform the data that we got so as to better satisfy certain assumptions of regression and so forth and so on. So we'll go through what those will be as we go. But intuitively speaking, these data have a certain or a certain skewness to them, and we might want to somehow model that skewness using a transformation of variables. Another example would be this data on protest events per day during 2020. And as you see, the COVID-19 outbreak begins, around February, and it really, it begins during this whole period. And at a certain point, right around January 1st of that, I guess it's that next year, you see a spike in protest events. But the key thing here is that the average protest event number is a lot different than the maximum. There's a certain skewness, just like we had with GDP. Like the most protest full day is a lot more full of protest than the average. And this is giving us an indication that we might want to somehow transform this variable to make it better behaved in some sense. We might not have an easy way to model something with such a strong skewness to it, but maybe there's a way we could transform the data so that there's less of that potential issue. And this is going to be relevant to the regression material as well, which we'll go through, we'll learn all of us together. So this is just giving you a sense for the fact that the data are skewed. And are there other cases that you can think of where maybe data could be skewed? Or any other examples people have?
Voting turnout by age.
Okay, can you say more? What makes you say that?
Typically people who are older tend to turn out more to vote, so it would be a right skewed.
Yeah, so the age distribution among voters might not be uniform, or it might not be kind of symmetrical in some sense.
Yeah.
Remember how the normal distribution, what we call the normal distribution, the Gaussian distribution, so-called bell curve, this has a certain symmetry to it. But in that case, it might not be symmetrical, so you might want to transform things in that sense. And that's a good example. Other examples, other thoughts that you can think of?
Income inequality.
Can you say more?
Because you can take the Gini coefficients, and some countries have really high income inequality and some have really low. And so, so it's really skewed because the United States has really large income inequality, whereas
Yeah, no, that's a great example. So you have income inequality where some countries have a lot more inequality than the average country does. So you have this kind of bunching around, for example, and also there's clustering of the data. So the European countries all have pretty similar income inequality, but then you have other countries like the US and potentially India and others where there's potentially a lot more. So those are all great examples. And I think a lot of our social science data are highly skewed in some way or have really fat tails, or they have features that might make them hard to work with. So these are just some examples that I thought of, like the contribution amounts to different candidates, which is complicated a bit by the cap on contributions, but if it was unlimited, some people would just give a lot more. You have growth rates, like some countries grow a lot in a small period of time. So for example, in the Chinese experience, you had some years where growth was just tremendously high, but that was a lot higher than the average growth rate. So you had a certain asymmetry to the distribution. And these factors make the data a little bit harder to work with. And you might ask yourself, what's the intuition? Like why do I say harder to work with? We'll talk more about that in the regression part of the course, but intuitively speaking, you can think about a really skewed distribution where you have some values really far over here to the right. In that setting, a few small data points have a super big deviation from the mean, and in many cases we're going to basically try to model the distribution using the mean, and use in these extreme points sort of make that calculation of the mean more sensitive in some intuitive way. Or if we do or don't happen to sample, let's say if we sample Elon Musk in our survey, our estimate for average income is going to be a lot different than if we don't sample Elon Musk, since most people don't have $100 billion in terms of net wealth. So the idea there is that there's a certain sensitivity to these extreme outliers that make the modeling process hard. So that's kind of the motivation for all this transformation of variables business. And the good thing is, so the key question that we'll work with, the key question is, if X has some distribution that I'll just call D, then what are the properties of G of X? We've already covered this, so you're already becoming masters. You're well on your way to becoming experts at some of the properties. So remember last time we talked about how to deal with expectations and taking averages of transformations. But today we'll review that, and then we'll talk about some new things as well. So these are just more examples of how the raw income, household income, according to the census, has this right skew. But when we take the log of that income measure, now it looks like we might be able to approximately model it by a normal distribution. So this is kind of motivation for making behaviors that are, in a sense, quote unquote, poorly behaved, well behaved by transformations. And that's why we have to talk about how to do this in a principled way and how to think about it in a principled manner. So if there are any questions, I should stop for questions. Is this making sense to people? Hopefully we're not moving too fast or too slow. We're always trying to find the sweet spots. So we've already done some of this. For example, we've already a question.
Behind the scenes, what does the law do to make abnormal distribution abnormal?
Yeah, good question. I like the question. So for those of you who can't come to class today, the question is, what's the intuition for why does taking the log make the abnormal normal, in a sense? I like the way you put it there. So the basic idea is, if maybe we can just go to, so I'll go to, well, let's do it on the board. So we have some income. So we have some income, like let's just say 10. So we have, let's just say we have these incomes. We have 10, we have 100, we have 1,000, and then we have, a billion or whatever that is. We have a billion here. So we have 10, we have 100, we have the distance between 1,000 and a billion. That's really big. It's a lot bigger than the difference between 1,000 and 100. But when we take the log of all these using the base 10, this would be 2 in the transformed space. So this is the log space. 10 becomes 2, and 100 becomes 3, and 1,000, this is 10 becomes 1, 100 becomes 2, 1,000 becomes 3, because we're saying so this is the definition of the log. We could talk about it in terms of the intuition for that too, but the basic idea here is the log of 10 in base 10 is 1. In other words, 10 to the power of 1 equals 10. And for this, we have 10 to the power 2 equals 100. And 10 to the power 3 equals 1,000. So these things that were really far apart in the raw space are now really close together. The difference between this number and this number in the transform space is just 1. but before it was a lot bigger. So basically what you're doing is you're distorting distances so that things that were really, really far apart on the upper end of this scale get squished together, but they get squished together differentially more than things that are really small. So the distance between 10 and 100, that's a pretty small distance, but the distance between, in the raw space it's small, but the difference between 1,000 and a billion, that's a really big difference, but when you log it, all these things become, they have the same distance. So you can think about it in terms of distances, how you're sort of squishing the things that are really big to be closer to the things that are smaller, and you're squishing those more than you're squishing the things that are already really small. So that's an intuition. Does that clarify? Yeah, good question. Other questions?
I guess the follow-up question is, in some of the critics to like quantitative surveys, people would argue that like log, when we log the variables, it loses its original meanings for it. From here is that you also change the original data structure, right? So what's the rationale or
Yeah, good question. So whenever, for those of you who can't be with us today and who are on the video, the question is, what about the fact that we've transformed the data so the scale is different? We've transformed the data so it's no longer the same as it used to be. We're doing an analysis, but we're not doing an analysis with the real GDP per capita. We're using log GDP per capita. So I think there are a few different answers for that. One answer would be I guess there are a few different answers. It might be really hard to predict. Well, we have an example of this in the tutorial part of the class, but in some cases, our model might be, in a regression model, we're basically trying to fit a model to the data. And if we have something like GDP per capita, we have a few countries with really, really high GDP per capitas. And in regression, we're basically trying to, what we'll be doing is fitting the data more to those really wealthy countries than to the countries that are less wealthy. So there's a sense in which on a statistical level, those extreme cases are really affecting the fit. They're really affecting the model. And when we take a log of this, the sensitivity to those really big cases becomes less pronounced. That'll be one case that's a bit more statistical. We want to kind of reduce the sensitivity of our modeling approach to those extreme events. But more than that, there might be other cases where the underlying theory is truly more appropriate to the log scale. So for example, what would be an example? An example might be using GDP per capita on the right-hand side of a regression. When we're using GDP per capita on the right-hand side of a regression, we're basically using GDP to predict something else. If we use GDP in the raw scale, then we're basically saying every dollar change is equivalent to every other dollar change. But if we take the log of GDP per capita, we're no longer making the assumption that all dollar changes are the same. We're saying that a dollar change around 0 is a lot different than a dollar change at a billion. So a dollar change between 0 and 1 kind of has more significant. If you look at the graph between the raw variable and the transformation in that case, it looks something like this. So there are decreasing marginal returns in this case. So whenever you think that there might be decreasing marginal returns of the independent variable of interest, logging that variable might be an appropriate thing to do on a theoretical level. Because in this case, like having $10 per day versus having $20 per day is a massive difference. But earning $1 million a day versus $1,010,000 a day is a smaller difference because income scales in this marginal fashion. So that would be another motivation for doing the transformation in this case. It's a transformation motivated by the marginal utility of every extra dollar. So does that kind of clarify? So there's a statistical reason and then there's a theoretical reason based on marginal utility. Yeah, Andres.
So maybe you can talk about this paper from last month in political analysis about how to on how to interpret log variables on dependent variables. And it's interesting because like sometimes as Connor was saying, we do care about like the logged version of the variable, but some other times we're doing it mostly for practical reasons. And we still want to convert back to the original scale when we interpret results. it turns out that it's not like as simple as it seems. So maybe that's something that might be of interest to you. I will share the paper. Maybe we can talk about it in the tea session.
Yeah,
It's an interesting thing, always keep in mind like what is the thing that you want to interpret. And it's like a very simple point, but
Yeah, no, great point. Definitely, please do post on Piazza. I think that would be really interesting to take a closer look at. Yeah, those are all great points. I'm not sure what else to add other than saying these will be continuing themes throughout the course, so I'm sure we'll have time to discuss and further refine our understanding. So I'll just keep moving since I want to make sure we cover all the content. I'll try to finish up in about 15 minutes. We might go. This tutorial for today is a little bit less long than the normal tutorial, so we'll do a little bit more with the slides. So this is something that we already know, and this was the law of the unconscious statistician. The idea that we talked about last time about how we find the average of some random variable that's been transformed in some way. So here, this bold E, that stands for expected value, which we talked about, and this G stands for some function. In this case, that function is assumed to be a deterministic function. There's another kind of function called a stochastic function, but that's not what this is. This is a deterministic function, like taking x and then squaring it. There's no randomness in the transformation. There's randomness in x, but there's not randomness in this transformation. And then we have this sum over all possible values. This is just exactly what we saw before. So we have this weighted sum of g of x, where the weights are equal to the probabilities. And if you have any questions about that, please do raise them, and we'll talk about it. We also have this continuous extension that we talked a little bit about too, so I won't dwell too much on it. It's here for review. And here's the intuition. We already introduced it, but it's good to talk about it, from a few different angles. So the intuition is this weighted average idea of g of x. And here's an example for you. So this is an example which I'm feeling like maybe we can do that as a practice problem or something. But this is how you calculate e of x for the binomial distribution. During last class, or maybe it was 2 classes ago, we talked about e of x squared, where x was a Bernoulli. But this is how you do that same sort of calculation for a binomial, which is a generalization of the Bernoulli. So this is what we have here, and this is all stuff that you know or are on the way to knowing or have started to learn or will continue to learn. And if you have any questions, definitely let me know. We also have this other problem though, and the problem is that this lotus idea. Remember, we want to figure out like what's the average log income, or what's the average value of something when we're transforming it. That's what this is, but then there are some limits to it. So in some cases, we might not care about the expected value only of g of x. We might care about the whole distribution of g of x. So we might not only care what's the average of the transformed thing, but we might care more about the whole distribution over that transformed thing. So this is it's the last day where we're really going into the nitty-gritty of the probability theory. So I know it's getting perhaps a little bit repetitive, but we're going to talk about how to do the transformation of variables in 3 or 4 different settings that you'll be able to use as a kind of weapon in your arsenal. Whenever you see hard problems, you can use those to confront those problems and confront those challenges. So the first case, so I guess first, before we go into this, I want to talk a little bit about different kinds of transformations. So we're taking x and then we're doing something to it. And some transformations are what's called 1-to-1. So the idea there is you have the original kind of set of values on the left, and the transformation brings them to some new value on the right. And the key thing about 1-to-1 transformations is that it doesn't kind of, in a quote-unquote, mess things up. It doesn't mess things up in the sense that everything over on the left gets mapped to one and only one entry on the right. So this is an example of that, where we have x, and then we're taking the square root of x, and here x is defined to be greater than or equal to 0. And in this case, 16 maps to 4, 4 maps to 2, 9 maps to 3, one thing over here maps to one thing over here. And there are no collisions of 2 things mapping to the same thing. That would be more confusing. And that's not going to happen. That's forbidden when we're working with a one-to-one function. So that's one kind of function. But there's another kind of function too, which you might have heard about in maybe your algebra or linear algebra or calculus or differential calculus classes. And in that case, it's not a one-to-one function, but now it's a many-to-one function. So the idea there is you have collisions now where two different things, when they get transformed, now all of a sudden take on the same value. So when you have this operation of taking something and squaring it, you have -2 and you have 2, and you square it, and now it's all of a sudden they're both 4. So two things that were distinct before now are no longer distinct with a one-to-one, or sorry, with a many-to-one or a not one-to-one function. So you can think about that. I mean, there are different tests you can do. For those of you who are on the Zoom, I'm trying to put some graphs on the board, but kind of. So in the context of a one-to-one function, if we have all the values of x, you know, you can use various tests, which I guess we don't need to get into for that, but there are ways of kind of trying to evaluate, is a function one-to-one or is a function many-to-one? In general, your best way of figuring that out is thinking about the nature of the function, and if you don't know beforehand, plotting the function can be good. You can use R to plot it. You can use other tools to plot it. But so this is important because there are different ways of doing these transformations of variables depending on whether the function that you're interested in is a one-to-one or a many-to-one function. And it turns out that the log transformation is going to be a one-to-one transformation over the domains that we're interested in. So this is basically the idea, and I promise that next time we're going to get into the data more. So we're going to get our hands dirty with the data more next time. But in the context of these one-to-one transformations, the distribution of the transformed random variable is actually extremely intuitive. And I've listed out the intuition for you all on the slide. I'll just read it because I think, hopefully it's clear. If you're transforming a discrete random variable in a one-to-one g, which is just that function, every discrete element of x gets mapped to another discrete element of g of x. That's sort of the definition for one-to-one. And therefore, the probability of g of x is just equal to the probability of x. So in other words, if you have some random variable x is the original thing. X is like income, and y is like log income. So if you have x, and then you have g of x, that generates something new. That generates y. And in this case, this is the notation for it. It's whenever you're working with these transformations of random variables, the most confusing thing of it is the notation, because you're working now with two different distributions. The first distribution is the distribution of y, and the second distribution is the distribution of x. So you have two different distributions, and in your mind's eye, you have to try to remember that there are two. And I've used notation here to try to distinguish it. So here, this p of y equals y, we're basically asking what are the different probabilities over the transformed values. That's this thing here. And then this is equal to this p of x. So now this is a new distribution. This is the distribution of the original value of the original random variable x. And we basically say for a specific value of y, if we inverted that, we would get a specific value of x, and let's take the probability of that. So I think this is best worked through for an example. So in this case, we have a binomial distribution and with these parameters, and we're trying to calculate the probability that y equals y for this transformation. So we have this case where over the support of x, this transformation is one-to-one, because the x's have to be positive, and over that domain, all of this transformation is a one-to-one function. Taking the square of a positive number is going to be one-to-one over that, over that area. So in this case, we basically say, this is basically what we'll do. We're going to take the inverse function. So the idea here is, it's kind of simple. So we have what we want to understand. What's the probability that y equals 4? Well, the probability that y equals 4 is just the probability that x equals 2, because we have x and then we square it, and then that's the new random variable. So we have 2, then we square it, and then we get 4. So the probability that y equals 4 is just going to be the same as the probability that x equals 2. And this is the somewhat complicated notation to try to express that. And so the basic idea here is the inverse transformation of taking something and squaring it is taking something to the, taking the square root of it. So if you have some positive number, you can square that positive number, and if you want to get back to the original number, you take the square root. So you have the square, then you have the square root. You have the square, and you have the square root. And these two functions work in tandem, and this is what allows you to calculate the probability of the new thing. So the probability of the new thing is equal to basically the PDF of the binomial distribution, the original binomial distribution, where you've put into that PDF the transformed value of y. So in other words, this is like a recipe. If you give it 4 for y, but you basically are going to take that 4 and you're going to take it to the 1/2 power. You're going to take the square root of it, and then you're going to plug in the square root of 4 into the PMF for the original distribution. So I know it's a bit of a mouthful, it's a bit of a mind bender, but it's actually very intuitive. Basically, you just use the original PMF, and you basically just, in your mind's eye, do that reverse transformation and figure out what value of x would have given you that value of g of x, and you just report the probability of that value of x that would have given you that value of g of x. So this is a lot of words, but what are your thoughts? Like, is it starting to make sense? We'll do some examples in a few minutes, but the basic idea is that we want to know the probability of the new thing, and we use the probability of the old thing in a particular way, and the particular way that we do it is we use the inverse transformation, and we basically say what value of x would have given me 4, and then I return the probability of that value of x that would have given me 4. And this is the way of getting the probability distribution over the transformed random variable. Are there questions? I feel like every time I say it, it sounds like a mouthful, but are there things that are unclear, or maybe with the notation, are there things that we should talk about? Is there an aspect of it that you think we should talk about again? We'll come back to this, since I know this takes a little bit of thinking, it takes a little bit of practice to get it down. And this is just our first exposure to it. So the first exposure always has the most uncertainty and the most, confusion, but the second exposure there's less, and the third exposure there's less, and by the time you see it a few times, you're going to be masters of this. Any questions, any comments? Okay, so it's about 1:53. I'll try to get through this pretty quickly because we're going to come back to it. So I don't feel as bad as I would otherwise feel about going through this quickly, because we're going to come back to this next time, and we're going to have experience working together to make this understandable as possible. So this is what we do in the context of those one-to-one transformations. Those were those really nice transformations where everything over here just got mapped to one value in the new space, and there were no collisions. The collisions make things a little bit harder, but in the context of discrete random variables, actually we can break it down together and we can make it work in an intuitive way. So in the discrete case, the intuition is going to be very similar than to before. So here, basically the idea here is, let's assume that income was discrete. Then we would basically say the following: to find the probability of log income, just add up the probability of all the values of income that become log income via G. Or maybe a better example would be, I don't know, there aren't many to one functions in social science applications, so it's a little bit harder to think about a good application. If you can think of one, please shout out and we can use that. But the basic idea is, if you look up here, there are in some cases like two values of x that map to the same value of y. What we're going to do is we're going to say, when we see 4, what we're going to do, very simply, very easily, very intuitively, is we're going to say, how could we have gotten 4? One way we could have gotten 4 is by having x take on -2. Another way we could have gotten 4 is by x taking on the value of 2. And the probability of 4, therefore, is just the probability that x takes on 2 plus the probability that x takes on negative 2, and that generates the probability that y takes on the value of 4. Very simple, very easy, very intuitive once you think about it a few times. So you're basically saying, I can get 4 by many different ways. Let's just add up the probability of all those different ways, and that gives me the probability of 4. And that's what we're saying here with this notation. I'll try to explain everything extremely clearly. We have P, that's the PMF, a symbol for PMF. And so here it's the PMF of y equaling y. Y is the new random variable, and that's big Y. And the little y here is a specific realization of that new random variable. And we're basically saying take the old random variable and sum up over all the different ways that old random variable transformed would be y. It's basically just what we had up here. The notation is a little bit funky if you haven't seen it before, and there are other ways of writing the notation. We can experiment with those together. But this is the idea. Are there questions about this? Is it making sense to people, or are there things that we should clarify? Here's an example. So let's think about this. Do I want to go through this? I guess so. So this, I promise we're getting towards the end, then we'll have a break. I feel like we need a mental reset. I feel like the mood is getting to that point. So maybe I'll go through this after the break. Maybe we'll just do high level and then we'll do low level. So the last thing I want to talk about, we're skipping over this for now. We'll talk about it either after the break or next time, because I think it's the time just for a little bit of theory, and then we'll go through that. So this is the case of continuous random variables. And before we were working with discrete random variables. And when we were working with discrete random variables, we could think about things in this nice way where things either mapped to each other in a one-to-one way or where they had these collisions. But now we have a problem. And the problem is things are more complicated. Whenever we're working with discrete random variables, things are easier. When we move to continuous random variables, there are these nuances that are involved. And the nuances are involved basically because this is just a visualization of how spaces, how kind of events in the continuous space in the old space, like events, areas in the old space are being stretched and smeared in a particular way in the new space. I know that's very abstract, but we'll talk about it as we go. The basic idea is with discrete random variables, you don't have the same problem with kind of smearing in a kind of continuous way. So the basic idea is when we have continuous random variables, things are a little bit more complicated, but we'll walk through it together. And this is just your first introduction, and we'll keep introducing you to it because that's how we learn. So this is just the formula. The formula is py of y equals px of g of inverse of y times this thing here. And we'll break it down just in turn, and then we'll have a break because I think we need a break. So py of y, that's just the pdf of the random variable y. And remember, y is just the transformation of the random variable that we have called x. And we're basically saying the probability that y takes on, the probability density that y takes on some value is just equal to the probability density that g inverse of y takes on some value according to the original thing. So this is basically the exact same thing that we had before. We asked ourselves, like, what are all the ways that you could generate x from y, and then just sum all those probabilities up. That's similar to what we're doing here, but now we're basically saying we have the original random variable x, and we're asking ourselves, like, what's the inverse, what values of y would give me a given value of x, but we need to make an adjustment for the fact that we're going to that probabilities in the new space are not, the probabilities in the new space are defined over sort of regions that are weighted differently compared to the old space. So remember, with the log, we have this distribution over here. If we just have x and then we take the log of it, the distances in the original space are no longer the same as distances in the new space. And I'm not really going to talk too much about this now. I'm just giving you the high-level introduction, and then we'll talk more about it later. But basically, we have this adjustment factor here to account for the fact that distances in the new space are different than distances in the old space. And this weighting term over here, this derivative term, is a kind of quantification of that in ways that are probably not right. It's not the right moment to talk about that. We'll talk about it again next time, and we'll give more intuition for it. This is just showing you the formula and talking about the different cases, and then we'll return to it again, and we'll get more experience with it. So this is the last case, and I know we've been through a lot, and I know people are probably getting sick of the probability theory. So let's do a mental reset, and we'll come back together in a few minutes. Let's come back together at 2:04, and then we'll talk more about this, but we'll make it with the real data. We'll use the real data, and we'll get some experience with these sorts of things. By the way, everyone should post your project data to the database once your projects are done. Let's do what that. Share it, also brings attention to your work.
wondering Halloween candies and stores.
Check it out in the library.
All right, let's come back together. Okay, one hint for everyone. There's a way to open multiple RStudio sessions. You might have figured this out already, but it took me a while to learn. In some cases, you might want to be doing 2, 3, 4, 5, 6 analyses at once, and you just don't want one RStudio open. You want a whole battalion of RStudios open. And there is a way to do that. It's simple, but I'm just telling you. Just go to whichever RStudio is open, and then right-click it in a new RStudio window. That will open up a new R and RStudio environment, completely independent of the other R and RStudio environment. One thing to note is that these kind of copies, sometimes if you right-click on these copies, sometimes it doesn't say, it doesn't say open new RStudio window. So you might have to play around with like clicking on different copies to find that new RStudio window entry. So that's just one thing. So that's one trick of the trade. You can open a whole battalion of R scripts as processes using various terminal tools. We don't really cover those in this class, but in the Making Big Data class, we talked a little bit about some of the tools. So for example, GNU Parallel, other tools for basically making your computer into a kind of cluster computing environment. So that's just one thing to keep in mind. There is a way to make your computer run multiple R jobs at once if you have a lot of things that you need to get done, and they can be broken up into smaller subunits. So keep that in mind. And also, it's possible to work in multiple RStudio sessions at once if you need to get more. If you need to, run an analysis here, but also run an analysis there, you can do that all at the same time. So that's just another thing to keep in mind. Other tricks of the trade. I think that's it for now. In terms of, let's just go to the data. So in the script for today, which is labeled probability 4, we have just an analysis where we're doing some hopefully straightforward transformations in R, just giving you the experience with that, giving you more and more experience working with the real data. So let's just go to line 87, where we're using data from this mass package. And this data is well documented. If we just hit question mark and then the Boston, we're basically going to work a little bit with this data frame, which is about housing values in the suburbs of Boston. And we're going to ask ourselves, do we have severe problems with skewness in some of the variables in the data set, or do we not? We're going to ask ourselves questions like that, and we're going to get to know the data, because this is the sort of thing that will become increasingly important in phase 2 or evolution 2 of the course, where we talk about statistical inference in addition to and supplement to the probability theory. So we can do things like take the histogram of CRIM. We might not know what CRIM stands for, and it looks like this is the crime rate per capita by town. So this is a data set where the unit of analysis is town. Remember, unit of analysis just means how do you characterize the rows in your data set? Is each row a country, or is each row a country year, or is each row a town? In this case, each row is a town. That characterizes the unit of analysis. And in this case, it looks like the crime rate in some places is a lot greater than the crime rate on average. So the average crime rate is about maybe 17 or so, and we can actually use AB line to plot where the average is. So AB line is going to be something that we can use to plot where the mean is. So AB line mean, V equals mean CRIM, col equals red. What this is going to do, and let's just say LWD equals 2. This is going to plot a vertical line at the mean of that crime variable, and we're going to color it red. And there is the mean crime rate. It's even lower than what I thought it was. The mean is like, what is the mean? Probably like 7 or something really pretty small. The mean is 3 actually, 3.6. So although we do have some towns with a crime rate of up to 80, the mean crime rate is 3. And this is a way for showing the mean and showing for the whole distribution together. AB line, you can also use it to plot horizontal lines. So if I just said H equals this, and then if I went and changed this to blue, I would have something totally different. Now I would have a horizontal line at 2 on that, or 3.6 on that scale, but now instead of vertical, it's horizontal. These are useful for making beautiful plots, which are important for trying to convey your story to your audience. Since people, a lot of people are visual thinkers, and it's good to communicate with them through great visualizations, through great explorations of the data in a visual manner. So those are a few things there. A B line also can be used to plot just general, intercept slope lines. So if you remember back, there's the formula for a line AX plus B, and that's basically what this is going to do. So A is going to be, let's just make A equals 0, B equals 1. What's this going to give us? We can ask ourselves, well, it looks like this, and we can reverse it. A equals 0 and B equals 1. What is this going to do? So basically, in this case, A is the intercept, and B is the slope. So it's A plus BX is really the formula that they're using. So this is just for plotting generic lines in R, and this could be useful later on. So I'm introducing it to you now, and you can use it to try to explore features, aspects of your data. Any questions? Any comments? So that's that. And now we can look at the transform variable. So the original crime variable, crime rate, it had that skew to it. There were some places that had a lot more crime than others. When we take the log transformation, now the distribution looks more symmetrical. So in some cases, we might feel more comfortable making a normality approximation to this transformed distribution compared to the original untransformed distribution, which had that skewness to it. But we might ask ourselves, well, how are other variables? For example, the median home value, how skewed is this? Is this as skewed, or is this less skewed? And we can ask ourselves that question. We can easily just plot the histogram, and then we can also plot the histogram of the transformed variable. And what are people's thoughts about this? Like, does doing the transformed variable seem to make this like more symmetrical or less symmetrical, or what are some of your thoughts about the median home values from this data set from the Boston suburban area? Yeah, it's maybe a little bit, but definitely it's less pronounced than in the original case. Like in the original case, we had this, and then in the transform case of that original variable, we had this. So that was a huge difference. Whereas for this, it's a little bit less clear, but maybe slightly more symmetrical in some sense. So we have to do, and in the second half of the course, we might actually talk about various statistical tests for assessing the question, which of these two is better characterized by a normal distribution. There are actually a series of test protocols, if you will, for trying to answer that very question, which is something your reviewers might ask too. Your reviewer might say, you use this normality assumption, but I don't believe it. Give me evidence for the assumption, and we're going to give you the tools, we're going to convey those tools to you for making that assessment. And then you'll be able to come at them and say, here is the quantitative data supporting the idea that the data are normally distributed. So you'll be able to kind of quantitatively convey, you'll be able to quantify those assumptions in the second part of the course, which will be important for that. So that's what we have there. And then I wanted to just run a linear regression because we're going to be talking about these a lot. And I've written down the formula in R for how you run a linear regression, which we haven't introduced those at all, but intuitively speaking, what we're going to discuss in the second half of the course. And this class today is sort of a bridge, if you will, between the first half of the course and the second half of the course, a bridge into that. So when we say regression, basically we're going to try to use, in this case, crime to predict the median housing values. Like and this isn't a causal analysis, but this is just purely on an associational basis. Are places where there's higher levels of crime associated with lower or greater median housing values? This is a question that is asked in the transportation economics literature. This is a question that might be asked in the gentrification literature. This is a question that might be asked in the policing literature, political science, sociology, economics, all the above. And we can use regression to try to plumb the depths of an answer. So we can basically say, how can we use crime to model the median housing values? What we mean by that will be made clear later on, but it's going to relate to something called conditional expectations. So far we've talked about expectations, But then in the next part of the course, we're going to talk more about conditional expectations. And this is what regression is trying to model. We're not saying what is the median housing value. Instead, we're saying what is the median housing value as a function of different levels of crime in the neighborhood. And this is what we'll be asking, and this is what we'll be answering. So we could do that linear regression, which is going to model that. And in this case, you see that there's a negative, what's going to be called a coefficient. So we look here, and we're going to summarize this regression, and we see here crime, and this is the first time that some of you may be seeing this. So I'm just showing you this because it's something that we're going to cover a lot in the next part of the course. But we see this crime variable. It has an estimated coefficient of negative 0.415. And basically the interpretation that we'll come to later on is going to be that as crime increases on an associational basis, there's an associated decrease in the housing values around that neighborhood. So this is just giving you an example of that. And then we're also going to talk in the future in classes to come about something called the R-square. The adjusted R-square and the R-square are very closely related, and basically the idea behind the R-square is that we're going to ask ourselves, how much of the variability in the outcome did we explain with the predictor variable? So in other words, how much is the how well do those conditional expectations soak up variability in the outcome? This is the question that we'll ask, and this is the question that regression then answers. And in this case, it's so the interpretation of this will be that about 15% of the overall variability in housing values is on an associational basis, kind of explained by this change in housing values, changes in crime. But we can ask ourselves, crime had that really fat tail. What if we try to actually log that variable in our model? Does it make the model more plausible, or does it make the model less plausible when we do that transformation? So we're going to log crime, and when you're doing regressions in R, you can actually just put in that transformation like this. There are cases when you have to basically put this I in there too. So this I basically says to R, take a transformation of this variable and return the output. It's going to be a little bit confusing, and we're going to struggle through it together. But the basic idea is that in R, instead of having to make an entirely new variable like log crime equals log of crime, instead of having to do that transformation and then redo our regression by changing this and making this log of crime, instead of doing all that monkey business of remaking a variable and changing it and changing it and changing it, instead of doing that, instead of going through all that rigmarole, we're going to just use the built-in operations of R, where R is, in a sense, behind the scenes going to be doing the transformations, and I won't have to directly create the transform variable. In some cases, it might be good practice to generate the transform variable for replicability's sake or for some other reason. But in this case, when we can just take the log of crime within the regression formula. This thing here is, we can ask ourselves, like, what exactly is this? This is the input to the LM function. This is something that we'll talk about, and it's called a formula. So there's something in R called a formula that basically tells your computer, how do I take all these variables and combine them together to form an overall estimate of something. And so when we take the log, we run the regression, and now we see that the coefficient on log of crime is still negative. And we'll talk a lot about this. I'm just introducing you to it now so that it's lightning kind of, it's an example of transformations, which is, I think, more interesting than the other ones. So we're doing those transformations, and now we're seeing that the adjusted R-square is a little bit higher. And we'll talk about what that means as we go, but basically we are explaining more of the variability in the outcome using log of crime compared to just the raw variable. This is presaging the importance of taking transformations of variables, random variables, when you're running some of your statistical models. You might have a better fit of the model when you transform the random variables that are in the model compared to when you don't. And the reason has to do with the marginal utility argument that we talked about, how increases in crime when there's no crime are a lot different than increases in crime when there's already a lot of crime. There's a marginal kind of a marginal change that's different depending on where you are with the baseline rate. So this is something that we'll talk about, and this is something we'll explore as we go. So that's pretty much all we have time for today. There are a few other notes in this document about transforming random variables. I think it's all pretty similar to what we were doing already, so I don't really think we need to dwell on it too much. Just maybe go through it and ask yourself, do I understand everything, or are there any things I don't understand? And if there are things that you don't understand, then come talk to us and come talk to your classmates. Post something on Piazza and we'll talk about it and we'll break it down. But this is what we needed to get through today, and we've gotten through it. So I guess I'll stop there. And if you have any questions, please do come talk to me. And otherwise, I wish you to have a good week. We'll talk again on Wednesday, and enjoy the cooler weather.